superconductors: the Meissner effect, magnetic levitation and suspension, and the flux trapping effect. In this demonstration, the black object within the styrofoam container is a single-grain yttrium-barium copper oxide high-temperature superconductor that is specially made in our own laboratories. Located next to the superconductor is an iron spoon. In normal room temperature, superconductors act like stones, having no interactions with the spoon whatsoever. This round object with a metallic luster serves as a powerful magnet. When the iron spoon is placed close to the powerful magnet, the magnet is rapidly attracted to the spoon. The smoking liquid that is being poured out on the superconductor is liquid nitrogen. Its temperature is 196 degrees below Celsius or 77 degrees Kelvin. The liquid near the superconductor undergoes intense boiling due to the heat that the liquid nitrogen absorbs from the superconductor. The liquid nitrogen becomes nitrogen gas, and the temperature of the superconductor drops gradually. When the boiling ceases, it indicates that the superconductor and the liquid nitrogen are in thermal equilibrium. This indicates that the temperature has cooled below the superconducting critical temperature, or 91 degrees Kelvin for the yttrium-barium copper oxide compound, and has established superconducting properties. In the process of cooling, the superconductor was not placed near a magnet. We call this cooling condition zero-field cooling, which means the superconductor is cooled with no outside magnetic field influence. After the superconductor has established superconducting properties, as the magnet approaches the superconductor, a strange reaction occurs. The superconductor is repelled. This effect is called the Meissner effect. Now we fix the bottom superconductor in place by pushing the magnet towards the superconductor. The magnetic fields from the magnet will pass through the superconductor, resulting in the so-called flux trapping effect. Now the superconductor and the magnet not only repel each other, but also attract. This combination of repulsive and attractive forces allows the magnet to stably float above the superconductor. This is known as magnetic levitation. If the magnet is slightly tapped, it will revolve above the superconductor, as seen here. When we pick up the magnet, the superconductor will leave the container and be stably suspended beneath the magnet. This is called magnetic suspension. Both magnetic levitation and magnetic suspension are caused by the flux trapping effect. When we forcefully separate the magnet from the superconductor and then slowly bring the magnet close again, the superconductor will be attracted by the magnet and be pulled closer. However, this reaction is not the same as two opposite poles of a magnet attracting and sticking to each other. The superconductor and the magnet both attract and repel each other, maintaining a fixed distance in between. If we turn the magnet over to the opposite polarity and then approach the superconductor will be shoved away. Moreover, the superconductor will tend to flip over in order to realign itself, and then be once again attracted by the magnet. In summary,